Yes.
So are you guys available maybe tomorrow in the noon time? Tomorrow at the noon time.
I have a smart automation demo.
Oh yeah, yeah. I'm thinking about maybe you guys can do this demo together with the smart home automation.
Oh, okay.
Yeah, you can do that. Yeah, because they already have the demo, so we'll have on the other side to do a similar demo. So just for your other people, if you don't know that tomorrow Professor Banerjee they have a course project demo in the noon. So we can team up with them to do a demo as well. All right. So yeah, are you interested in a demo? Yeah. Yeah, are you interested in doing a demo
Tomorrow?
Tomorrow's
Tuesday. Maybe. What kind of demo?
So it's like course project demo you have done. So what you can do is maybe bring your computer and we can set up a monitor that you can play your videos.
Yeah, I think I can tomorrow.
And explain to them. So I think it will be fun for them to learn from your project, and then they can give you some comments.
Sure. I'm not sure I can bring all the equipment. I can show the video.
I think you don't need to bring all the equipment. Just show them the video.
Yeah, I can show them the video. I can't show them for replay.
Yeah, and explain what's the
what time?
Noon, from noon to 1:30.
Noon to 1:30. Where?
The location is the same as the IT events.
IT.
Yeah, I think it's near the department. It's on the third floor.
Third floor IT.
Yeah, third floor in the high tea. So I think every month there's a high tea event.
Okay.
Yeah. All right, let's go.
Okay, so hello everyone. We're here to present our topic. Our project is called QuadTRON, Quadcopter based target recognition and certification. So basically, I want to make it quick because of time. So basically, what we just did was we developed a system where we can actually detect images of people or objects in real time on chip on board processor running or microcontroller running on drone. So basically, so why did we do this? Well, what's interesting about it? Basically, it has a lot of applications. Basically, disaster management, but it also has some other applications as well. Disaster management, like you can see, for example, the issue that happened at the Nepal disaster, and so disaster management and detection is really it's quite an important area. There's also some other areas to where it can be applied to, like it's like agriculture, railroad operations, and some other areas. But that's so move on to the next. Part of the motivation was just skip. Yeah. So part of our goal. So why is this important? So it's important because we wanted to change certain things. So the status quo right now, it's not that you can't do this now, but to do this now is very, very expensive, right? It's expensive, and we have to bring out the cost. So if you look at the cost of a typical setup, this is what you have, and then you have what. So we have to build our own custom-built solution, utilizing the best of, or optimizing the best of everything we could, and then trying to see if we could get something close to like near real-time. So this is the hardware. We have the drone itself. It's programmable and very flexible. It has an inbuilt open source autopilot and stuff. And then we also attach some other things. So we also put the Raspberry Pi in it for some of the processing we're going to be doing. And then you have the thermal camera, regular camera, edge radio for communication. Yeah.
So basically, this is the drone. That's what we had. No, we have that. That's what we had in the out of the box. and this is the stuff that we attached. These antennas, these are just showing you two settings that we can put the antennas in, the Zigbees. The new ones we can put at the back. This is just for show right now. We haven't used this at the back so far. But this is the main setting at the front in one of the USB ports of the Raspberry Pi. And then you can see wires going down, and these are the two cameras that we have. This is the new Lepton camera that we have with a 25 degrees field of view.
So did you test it?
Yeah, it gave us really
We
good
have some
results.
results.
And this is the Raspberry Pi camera module. It's a 5 megapixel camera that gives you 720p
Yeah, it's something.
video, and it's really good, but we haven't really worked with this one yet. We're still trying to figure out what to do with it.
Okay.
But this is going to be our secondary camera. This is a battery pack to run the Raspberry Pi, and this is the original battery for the drone. And that's pretty much it. There's a Pixhawk in here, which gives you the flight data and everything. So we've connected that to the Pi using these serial wires, and they communicate with each other using MapLink. We're gonna discuss this a little later. And this is the GPS. It comes down and goes up.
Yeah, and it breaks easy.
And it breaks easily.
Yeah, we have to
So
replace that.
we broke one
Yeah, we broke
in the
it.
first flight, which was actually toppling off. Yeah, this is just we just discussed this, so we're gonna skip this. And Amar's gonna come in and talk about the software components.
So, to make this work, we need to be able to communicate with the thermal camera to get imagery from it. Getting imagery from the visible camera or the RGB camera is simply straightforward. There's an SDK for that. You get individual frames. You can get a recording. No biggie. So that's simple. But the thermal camera, it's actually a tear down camera from a FLIR one, which is a kind of a device that you attach to your iPhone or your Android phone. So they have a Spark Fun, actually, Pure Engineering, yes. That's the name of the, there's actually 2 or 3 guys who made the company. So they have a breakout board for it, so you attach it, your module on it, and you connect your module using I2C and SPI ports. So those are the 2 methods of communication. I2C is used for controlling the camera, like setting AGC and other stuff on it. Okay. There are 2 temperature sensors on it, one on the housing and one on the camera module itself. So you can actually get those temperature readings for calibration as well. We connected it to our Pi's GPIO ports, and we wrote our own device driver for I2C and SPI. There was some example code provided, but we wrote a much better driver ourselves, and we are contributing open source to their driver as well. So we are writing their driver at this point in time. They specifically asked us to do it because our results were better. It had its own problems, still has its own problems. The module is actually plugged into it, and sometimes it becomes loose. It was not meant for flying, but and we're coming out with interesting ways, putting a rubber band or something to make it a stable.
It's like a 40-60 thing. Like 60% of the times it'll work, but then 40% of the times we fly the drone to the desired altitude, and then we realize that the camera's turned off, so we have to bring it down, open the whole thing, and then press it in.
So what's the problem there?
It's not meant for this functionality, so it's kind of loose in the housing.
If it's fixed at one point,
Why
even if
not
you're moving
why
with it?
not just solder them together?
right?
Because it's too sensitive. I think if we bring it that close to the heat, it's gonna burn.
You're right.
It's extremely sensitive. Are you gonna?
Yeah, it's okay. They can handle it.
Oh, you're gonna take out the camera.
Yeah, no
Okay.
problem. It should be interesting to see.
So this is what we have to do every time it shakes.
Uh-huh.
So
We
you
have to
can
take it out.
actually take it out.
And put it back. Right?
Right.
If anyone wants to see the camera, this is the new Lepton.
Make sure you don't have electric charge.
Yeah,
Otherwise
make
you
sure you're not
blow out
standing in
$300.
charge.
Yeah.
Okay, you're here.
Yeah, I will in the lab, so if anybody wants to, they're more than welcome. So I'm gonna quickly put it back. Been doing this for days, so I'm getting pretty ninja at it.
And that's just,
Yeah.
you say that's a regular camera?
It's
This
a
is
thermal
that's the
camera.
thermal.
It's the thermal camera. This is the thermal one.
The other one, it had everything made for it, like the casing
That's
is actually made
why
for the
like this.
camera.
So
So
we
it
made the case ourselves too.
Yeah.
It took a while, but then we had to solder the wires and so many other things that we are not experts in, and even writing device drivers or those kind of things. I haven't done this before, and this was our first time to kind of fiddle with these kind of things.
Yeah, for about like 2 or 3 weeks, we had problems with the camera.
Just
we
the
realized
camera.
We're just gonna solder it. So
So
yeah.
that was one of the key challenges. Anyways.
What's the resolution?
Oh, that's the
69.
interesting part. Well, coming to the resolution, when you say resolution, it's kind of, well, in this case, it's kind of a tricky question because the number of pixels we get is 4800, 80 by 60. That's more like a Windows icon.
80 by
80 by 60 pixels. That's it.
Wow.
Right. But here's an interesting part. When you get those pixels, those are not actually pixels of images. Those are relative temperature values. So if you have the housing temperature and the camera's module's temperature, so the housing temperature would reflect the environment temperature. And you can use that to kind of calibrate what the actual pixel temperature value is. And then you can upscale the image and kind of do some interpolation. We are trying to do that in our classifier, and we're getting there. We only got it working on Saturday, so it's not best, but it works. So we'll show the results.
Okay, good.
Anyways, let's move on. Right. So our classifier is basically MSER. This is one of the papers we saw. There is a related one using low resolution thermal imagery to do something. The idea is simple. If you want to detect somebody in thermal, just do a blob detection. So based on if the drone is flying say 20 meters up in the air, an average person on the ground would have certain blob size, right? And certain skin temperature. So the temperature would be somewhere between skin temperature and the environment temperature, not below or beyond. So we can use we are actually using some filtering and the blob size filtering to kind of do some detection. It's been working pretty good so far. Then we so this is kind of like hotspot detection. So we're not using background subtraction or those kind of things. We don't have body features, so we cannot use a hard classifier. So we have to come up with a very custom designed classifier for it. So anyways, then we had to use some implement some messaging protocol because we are getting this data from it and we need to send it back to the base station. Zigbees have their limitation. The maximum payload size for one packet is 100 bytes. And we had image which we wanted to transfer that was about 6 kilobytes, the resulting JPEG image. So we had to do our own fragmentation and packet reassembly. Then we had to implement per sender buffers on the receiver side because if the packet is coming from one person, we need to store it in a separate buffer. So that was a lot of overhead we had to do. So one of the key challenges there as well.
What do you think the communication bandwidth is not enough?
Bandwidth is fine. Number of the bandwidth is about 150. The new radios are 200 kilobits per second. But the problem is one packet can only take 100 bytes. So it can take about, I don't know how many packets from different centers at one time, but one center can only send 100 bytes. So we divide our payload into chunks, and then we send them off, assign a frame number to it, and at the receiving side, we only look for a terminating flag. Whenever we get it, we take the buffer, reassemble, and then ship it to our application. And the good thing about these Zigbees are they have their own inbuilt mesh networking. So we just send a broadcast message, and it reaches everybody. We don't have to take care of the mesh network itself. So we're using two modes of communication. One is inter-UAV communication. Is just it sends the drone states. By state I mean altitude, location, airspeed, ground speed, and if somebody was detected or not. And that's low fidelity data. That is broadcast. We don't want to broadcast image data as well because that would put a lot of strain on the system. So on a one hop, we broadcast state information and we unicast every drone unicast imagery and state data back to the base station. Unicast is fine. That can work fine. So we can send more data. We develop a frame grabber, which what it basically does is you get these are two cameras. You get two imageries. We're trying to save as a recording on the flash memory as well. So it records on for the RGB camera. It records on 25 frames per second, and the thermal camera has a 9 frames per second FPS. So they do their own recording, and then we selectively get a frame from each of them in one every 0.5 seconds. So that's the frame rate for us when we want to process images. To do that, to be able to do that, we needed to write our own frame grabber. So because you cannot do 2 things at one time unless you do something of your own. Then our base station, what it does is it gets the packets, assembles them, and shows it nicely on a graph or drone, which we'll show you in a while. Moving on. All right, moving on.
Yeah,
I discussed everything almost. So this is overall architecture, overall design. I'm sorry, I'm just walking around. The ground control station has a Java app. We want it to be platform independent. It uses Zigbee radio only. That's the only hardware that it uses. It sends periodic beacons to the drones as well. The reason for that is one that it could see that okay, I'm still alive and I'm still in range of the GCS, the ground control station. Secondly, the Raspberry Pis do not have a real-time clock. It doesn't come with it. You can attach one to it with a Solana. There is an RTC unit, but these ones didn't have, and we didn't know it in the beginning. So what we do is in every beacon we set a timestamp, so the drones can synchronize their clocks. The reason we need to have synchronized clocks is when we're doing recording and recording flight and imagery, we record timestamps. And if the time is like a day earlier, then everything falls apart. So there is a drift, about a second or 2, but that's okay. It's not mission critical. All right, moving on. So this is the UAV agent that runs on the Raspberry Pi. What it basically takes the image from the thermal camera using a frame grabber. It takes two images from the RGB camera as well. Then it does frame recording and then takes one of those frames, sends it to the flight retriever and recorder. What this guy does is it takes the state information from Pixhawk over the serial port, takes 2 images, makes a nice packet out of it, and assembles it for delivery. Then, can you go to the next slide? From this packet, the 2 frames, we have a thermal frame, we have a RGB frame. Right now, we're not using the RGB frame. We're only using the thermal frame. The thermal frame, we have the data is in OpenCV matrix form, so we directly feed it to MSCR, which is a blob detector. So the blob detector basically tell us, okay, I detected these blobs, and the blobs are of different sizes. So we do our own filtering to see, okay, if this blob is a person, and we set a flag in the original packet, which was assembled for delivery, saying that, okay, this is the detection result, and these are the coordinates approximately in the picture where the detection happened. And then the ground control station can basically draw nice bounding blocks on it and say that somebody was detected. So there's, right, so this is what image processing looks like. We get a frame of this size. Then we kind of enlarge it, we scale it, and then we run blob detection on it. Well, it's not visible here, but there is it's a blob, and there's some surrounding parameter lines, black lines on it. So it's kind of a detected blob here, and we determine the blob size, and then we do our filtering. This is what our ground control station looks like. We have the drone information, number of heartbeats, and airspeed, ground speed, altitude, and if it is armed or not. We don't do detection when it is not armed. So you have to put your drone in armed mode and then fly. If it's just standing there, we don't do it.
So when the GPS works, the map works with the GPS of the drone. So
right.
Wherever you get a lock on the GPS on the drone, it's going to show the drone over there.
Right.
The animated drone. And then if...
Right. So whenever a person is detected, it kind of like shows over here that, okay, person detected.
Flashes.
Yeah, and we couldn't do it today, but the plan is to, before the final report, is to kind of annotate the map with images whenever a person is detected. So we'll be putting a thermal image and an RGB image. Okay, this is the image. Probably there could be some false detections. They were with our case, but there would always be some false detections.
And these images are kind of like a live feed. Like every few seconds, you see a new image that is being that was just sent by the drone. So this is happening in real time. We're going to show
like
you
a first-person view. This is their FPV image. Okay. Right.
All right. So we came up with a bunch of scenarios to test the whole thing. For Earth, we had two scenarios: earthquakes and floods. We couldn't do testing for floods because we were going to do it in the swimming pool at the rack, and it wasn't available at the times that we were. And for earthquake, it's basically just on-ground testing. Then we have different altitudes. We tested at 5 meters, 10, 20, 30, and 40. 40 was the maximum we went. Then we have different weather conditions that we were simulating. For example, what kind of images we get when the object or the person is standing in shade, and what happens when the person is standing or sitting down in a sunny environment, because the surrounding temperatures have a huge effect on the way we detect it. The system, as of now, is not capable to function in rain because everything is exposed, and if you fly it in rain, it's just going to fry. Then we simulated 2 times, the daytime and nighttime. We did testing in both times. Then there were 3 kinds of surfaces. We haven't tested water so far, but we've tested on grass and asphalt or concrete. These are the 2 places. What this shows is we had our subject Nonso walk from here to this point. This was 20 meters for some speed testing and different things. But most of the testing was done in the quad, and the rest of it is going to be done at the pool. Then there were different kinds of movements that we were testing for. For example, the object is stationary and the drone is moving over it. The second type was the drone is stationary, but the object is moving either towards it or away from it. And then the third one was both the drone and the object are stationary. And we've already talked about.
So you just test both drone and they are moving.
Yeah, we made him run.
We actually we made him run and
Couple of
jump
times.
around. So these are just the 2. We are calling them prototypes because in the beginning we were working with the first camera, the basic left-hand camera, and now we have the second camera. So that's the prototype B that we have. These images are just showing you the differences between the 2 cameras. The new one has a 2x zoom. It has a 25-degree field of view. The other one had a better field of view, but at the same time, the results were really bad. These are the 2 cameras. This also had a shutter, so we didn't have to do the flat field correction. Yeah. This one doesn't have a shutter, but it's not a big deal. At the beginning, before the flight, we just put a black object in front of it and do the FFC, and then we fly the thing. So that's just to have better results. Now let's talk about and look at some results. These are for prototype A. These are also done at the quad. This is me and Amar flying the drone, and this is actually Nonso. I think this is Nonso, and this was someone walking around on the path.
So how do you detect that it's not so?
From memory.
We knew.
These tests were mostly done at 10 meters, and the drone was flying around at approximately 2 kilometers an hour. Sorry, this says miles an hour, but it was actually kilometers an hour. Okay. That camera gave us a lot of noisy data, because the resolution and the field of view and the zoom and everything, it gave us a lot of noisy data. And this is actually an image of the grass at the beginning of the flight. So
is that a thermal camera or is it regular?
that's the thermal. Yeah.
And the previous one was what?
Thermal.
Yeah. We get monochromic images, then we apply things to it, and it gives us.
We have raw
Color
data.
camera.
We can make pixels
Yeah.
any color we want.
I've already talked about it. Oh yeah, we tested it over the pool for flood scenario, but it actually did not give us anything. The reason for that was because most of the body, when someone's swimming, is underwater. Just the head is showing, and you can't really detect it because
Right. The
Yeah.
water acts as a thermal.
even if there's like a half an inch layer of water above the body, since water is also reflective, and that day was extremely sunny when we were doing this, so we didn't get any results.
We have an image for the
Yes, yes, we have.
We have an image.
Regular unit.
No, not regular
You
units.
have
All the flood ones, we didn't put those in because it was just showing us an outline of the pool. It wasn't showing us anyone.
It was
inside.
just all pink.
Yeah, the whole water body was pink, and there were at least 50 people inside the pool at that time.
Yeah, but it's also okay to show people the failure image, right?
Yeah,
Yeah,
there will be a couple of fair images.
So
we
they show
actually
the
gave up
data.
on that scenario for that
We have
camera.
all of the data.
Yeah, that's great.
Yeah. We're gonna do the flood scenario for the new camera again. So we're gonna
Yeah,
put
so
those in the
just
report.
remember to record all the data, even if the failure data is also
We
important.
implemented a black box on it. So
Okay.
even if the drone is destroyed in the air, you get the flash memory card and you get all of the data. Everything is in there.
So everything's stored on board. Okay, continue.
Yeah.
Well,
This is when we were doing the blob detection. You can see we've used the same images that we did in the last slides. You can see that it's making different blobs based on the temperature readings, and it's telling us where the person is. But for noisy data, that's the problem with this camera. There was a lot of noise, and since this is not a perfect way of detecting people, it's gonna give you a lot of bad detection.
And we're working on it.
But it's still a work in progress. Now let's talk about the prototype B. For this, we did a lot of like organized testing on Saturday. So yeah, this is the first scenario that we tested. We were calling it an earthquake. The surface that we were using was grass. It was daytime and it was shady in the quad. That's Nonso laying down. With the maximum surface area revealed. It was approximately, since he's like 6 feet tall, he was opening his arms and legs. It was probably about 7 by 3 feet. The object was stationary, so was the drone. We were just like moving it perpendicular to the surface. These are at different altitudes. The first image is at 5 meters, the second is at 20 meters approximately, and the third is at almost 40 meters, 39 or 40. So you can see that with the new camera, the results are amazing. Like you can even see the face is, hotter compared to the rest of the body that's covered by clothes. Now, the next test that we did was we reduced the surface area of the object. So Nonso actually sat down like a ball, and so the approximate area that was visible to the camera was pretty much 2 by 2 feet. And these are also at 3 different altitudes. This, by the way, is Amar, and this is me. In the image, I was flying the thing, Amar was controlling the ground.
So what's on the left side? The big
This is a tree.
Okay.
Yeah.
But since we are at a high altitude, the average person size should be small. We can safely ignore it. Our classifier ignores it.
Have you looked into other literature on human body information?
Right. That probably doesn't really apply that much because we did.
See the difference?
The problem with that is they try to do some feature detection of different body parts like upper body, lower body. Usually they do upper body.
Do they do the thermal?
No. For thermal, for thermal there is a paper doing MSER. That's what they suggested. That's what we're doing.
See the problem with our approach and normal approaches?
It's doing hotspot detection, which is block detection.
But actually, the problem here is actually what you're testing. Actually, the environment is good, right?
Yeah.
So if really is earthquake, I guess there's going to be a lot of
Right.
hot spot there.
Right.
So
There
there's
would
a
be.
lot of false positives.
There would be. But then we're doing another kind of filtering.
And
We're filtering based on the temperature.
And another thing is just like if you are only a small block, that's easy. But what if like Nansu is laid down there?
Yeah.
So how many people you will detect?
Right. That is a challenge.
Of course, you
That
will
is a
see.
challenge.
You see the
It will
signal,
be.
yeah.
In some cases, he will be noise. In other cases, the other person will be a noise.
Yeah.
So we cannot do everything. So what we're going to do, our future work is to use thermal imaging as area of interest only, and use the visible image camera image because that's 5 megapixel, larger image.
I think
Do more of
can do is because thermal at least you can detect hot spot, right?
right. That's what I'm saying.
That's telling people, okay, you probably should take a look what's going on.
That's what I'm saying. Area of interest. So without instead of using the whole picture for detection, just use a few cropped parts based on the thermal image, and then run your favorite algorithm on it. So that would be a good future direction, because this doesn't work all the time. This is not supposed to work all the time. You're only getting one kind of information, that is temperature. You're not getting 3 colors. So RGB has a thing where you have 3 different colors, and you can kind of do some sort of subtraction, those kind of things. Here you don't have much data, and this is 80 by 60. So I don't expect it to be very promising. We never thought it would be promising. We are fortunate to get this.
Yeah. Let's try to finish in 3
Right,
minutes.
right, right.
because I wanna
And
let you
So,
know.
this was, we changed the surface. Nonso was standing on an asphalt path in the middle of the quad, and it's at the same different altitudes, 5, 20, and 40 meters, and you can see different detection results. Move on. Then this was the moving object and stationary drone test. In the first image, Nonso was moving away from the drone. He was moving that way at about 5 kilometers an hour. In the second image, in the first one, he was caught in 3 frames because the speed was pretty low. In the second one, he was only caught in the first frame, and that was it. Because by the time the second image was taken, he was already out of frame. That was at 7 kilometers an hour, and the third one, he was running away from the drone, and you can see that he was caught right at the top of the frame, and that was at pretty much 50 kilometers an hour, and the altitude was kept the same, 20 meters.
How fast can it go?